Already, we're picking up where we just left off, talking about halogenation as far as addition reactions to alkanes. This is section 8.9 in the third edition book, and it should be 9.9, I believe, in the second edition book. So just make sure you're following along in the correct chapter. So now earlier in the chapter, we talked about hydrohalogenation. Halogenation is similar, but instead of adding a hydrogen and a halogen, now we're just adding two halogen atoms here. So the classic addition is just take an alkene, you put it in chlorine or chlorine gas or bromine liquid, and you end up with two chlorines, added on both vinyl positions there on the alkene. And so we kind of talked about this very briefly, but this is a key step for if you're going to make polyvinyl chloride or PVC, which is a very important plastic. You make the dihalogen, so the dichlorine compound, and then you do a single elimination that gives you the vinyl chloride. Once you have the single elimination product, then you can polymerize it, which is something we haven't talked about, but you can take these alkenes and they do polymerization. Now, practically speaking, you can only do halogenation with chlorine or bromine. So we'll only really talk about chlorination or bromination. Iodine isn't reactive enough, and then fluorine is like too reactive. So chlorine and bromine are kind of in the Goldilocks zone where it's just right, just fast enough that it occurs, and then not too fast that it runs out. Basically, like fluorine will rip the thing apart, and it might as well just be burning at that point. You're not going to really control what product you get once you start the fluorination process. Now, as far as regioselectivity, halogenation is different from what we've talked about before. Most of the ones we've talked about so far are syn addition products, but with halogenation, it's actually anti products. So if you take this one here and you add bromine to it, you're going to end up with a trans bromo product. So one is going to be on top, the other one's going to be on bottom. And the opposite is true too. The other one's on top, then the other one's on bottom. And these end up being the same compound because they're meso to each other. They have this axis of symmetry. Okay, now, right, so what was I saying? Oh yeah, so halogenation is anti-addition. And if you remember, like the reason something is a syn addition reaction versus an anti-addition reaction all boils down to the mechanism. So whenever you see these little details, you think, oh, there's got to be something in the mechanism that makes that happen. Okay, so this is how the mechanism works. So it starts with basically you add bromine across the double bond. So bromine itself is nonpolar, but it's a very big molecule. And big molecules are what we call polarizable. If a nucleophile approaches it, then it's going to push the electron density away from it. And so it can and create a dipole, sort of like an induced dipole, if you remember talking about like dispersion forces in the past. As the nucleophile approaches, the electrons shy away, and that leaves you with a partial positive side on one bromine. And sure enough, that's exactly what happens. So when we draw the reaction arrow, we have our pi bond act as a nucleophile. It attacks the bromine. Either of the bromine atoms is fine. And then the bromine-bromine bond breaks. You lose a leaving group in the bromide, and that produces our product here. Now, hold off on this real quick, because we're going to talk what this looks like here in a second. Okay. So, so even though like when we normally do this, we'd expect to form a carbocation, we know that we don't get syn addition. We only get anti-addition. So if we just had a true carbocation, like what this looks like here, we would predict, syn addition could occur, anti-addition could occur. That's not what happens. So that must not be what the intermediate actually looks like. So instead, what it is similar, or what it is consistent with, is what we call the bromonium ion. So the bromonium ion, rather than like being bonded to one of the carbons, instead acts as though it's bonded to both carbons at the same time. When this happens, basically it sits on top of the alkene, or you can think of it sitting on the bottom as well, but it sits on top of the alkene, and it basically prevents the other nucleophile, the bromide nucleophile, from approaching from the same direction. So the bromine, sitting on top as the bromonium ion, the bromide that's going to come in and be our second halogen atom, that can only approach from the bottom. And so that's why we get this anti-addition. This bromonium ion has the bromine on top, so the bromide, the second one, has to approach from the bottom. There's no no other choice. So this is the mechanism here. You have first your nucleophilic attack of the alkene, the pi bond, onto the bromine. You have the loss of the leaving group, the bromide, and at the same time, one of the lone pairs on the mirror bromine forms a bond with the other carbon. That gives you this bromonium ion, where the bromine is bonded to both of these carbons, and it bears a partial positive charge, or a formal positive charge, excuse me. Now, once you have the bromonium ion, the bromide is going to attack from the bottom at this point, and this is where, so we have the attack of our nucleophile, and we break the other carbon-bromine bond, getting rid of this formal charge here, and that gives us our final product, the anti-dibromine product. So yeah, so again, this is going to be stereospecific because whatever the stereochemistry of your alkene is, so if you have cis or trans, that's going to determine what the stereochemistry of your product is going to be. So if you have cis-2-butene, then you're going to get these products where basically you have one on top, one on bottom, one on bottom, one on top. If you have the trans-2-butene, then all of a sudden this is going to end up being a meso compound because you see that you have this mirror plane of symmetry here in the middle. So yeah, so you can see that whatever the stereochemistry is here, that's going to determine what your stereochemistry ends up here. Now, that's for halogenation. That's where you get two halogen groups. But there's also halohydration or halohydrin formation. So halohydration is like a combination of what we've talked about already. Basically, you're going to get a halogen added on, usually bromine, and then an OH group on the other carbon. And this is actually pretty simple because the mechanism looks exactly the same. You start from the bromonium or chloronium ion, like what we had with halogenation, and then that's subject to a nucleophilic attack. This time it's just from a water molecule rather than a bromide. So yeah, so and then of course you'd have a proton transfer to get rid of this oxonium ion over here, and that would give you your final product. So you'd form this one and the enantiomer, because of course you could also form the bromonium from the bottom, just keeping that in mind. Now the way that you can make sure that this occurs is basically just by using water as a solvent. Because there's going to be so many more water molecules around than bromine atoms or bromide ions, it's just like probably the water is going to be there just because you have more of those molecules floating around. So now I already mentioned this here, but once you form this oxonium ion, it's going to be deprotonated by just another water molecule in solution. So this gives you what's called the bromohydrin product, which is just, again, you have a bromine on one and a hydroxyl group on the other. And here, you know, if you use chlorine instead, it's the same thing. It's just instead of bromine, you get a chlorine. And this is what's called a chlorohydrin here. Okay. Now, we didn't have to worry about regioselectivity for bromination or halogenation because those, I mean, you just add the same thing. So there's not really going to be a preference. But halohydrins, halohydration is regioselective. So you have the halide is going to add to the less substituted carbon, and the hydroxide is going to add to the more substituted carbon. So in this case, like we take this alkene here, clearly the left is more substituted, the right is less substituted. The bromine is going to be added to the less substituted, and the water, the OH group, is going to be added to the more substituted. So you can think of it as like Markovnikov for the OH and anti-Markovnikov for the halide, if that helps. Now, the reason for that basically is that the water is going to be more likely to attack the more substituted carbon because that's a more stable positive charge here. I think this is on the next slide. The more substituted carbon has more cationic character because it's a more stable carbocation, whereas the less stable carbocation, or the less stable, excuse me, the less substituted carbon is less likely to be able to form a carbocation. So again, regioselectively, you're going to add the OH to the more substituted carbon, the bromine to the less substituted. Was there anything else I wanted to say here? Yeah, that pretty much just explains it there. Okay, and again, these mechanisms you will need to know. So just make sure you're kind of following along as we do the mechanism. The only difference, the only reason I didn't stop and go through this one is because We just went through it with halogenation, but we can talk about it just to make sure we're on the same page. Again, you form the bromonium ion, same, same, same. Now here, rather than having the attack of the bromide, now the nucleophile is the water molecule, forming our oxonium ion. This oxonium ion is then deprotonated in water, and that's how you get your bromohydrin in this case. Okay, next up, dihydroxylation. So we talked about hydration before. That's where you added a hydrogen to one and a hydroxyl to the other. Dihydroxylation just means you add two OH groups. So you can basically take ethylene and turn it into ethylene glycol. And so yeah, it's just the two added groups are OH and OH. So there's two different types. There's anti-dihydroxylation and there's syn dihydroxylation. So anti-dihydroxylation is a two-step process. You get a peroxy acid here. We'll look at a structure of what that means. It's basically a combination of peroxide and carboxylic acid. That forms an epoxide. Once you have the epoxide, you just react it in acid and you form your diol, your dialcohol. And that's going to be trans because they're added anti to one another here. Okay, so how do you make the epoxide? Well, again, you treat it with what's called a peroxy acid. And there's two ones that you get used the most, the peroxyacetic acid, which is just acetic acid. And then rather than an OH group here, this oxygen in the acetate is bonded to another oxygen, which is bonded to a hydrogen. So peroxyacetic acid. And then this guy here, don't worry about it, metachloroperoxybenzoic acid. We're just going to abbreviate it MCPBA. All you need to know is that either way that you do this, whether this is a methyl group or this metachlorobenzene group, what happens is you form this epoxide here. So the way that this happens is the pi bond is going to attack the oxygen. So you're going to form a one carbon-oxygen bond there. Then the oxygen-hydrogen bond is going to break as well. And that is going to actually form the other carbon-oxygen bond. So just kind of, if we're focusing in on the most important part here, that's this part right here, where again, the pi bond attacks the oxygen. That forms your first carbon-oxygen bond. Then the oxygen-hydrogen bond, that is going to attack the other carbon and form your other carbon-oxygen bond. I hope you can see just from this here how we get to this epoxide group here. Okay, now just to clean up everything else, this oxygen has to leave, right? So that means that this is going to form a new pi bond here, and then this guy comes over here and picks up this proton, leaving you with a carboxylic acid. So this is how you go from an alkene to an epoxide. Now this mechanism isn't particularly important, but I hope you're able to follow along with it as we write it out. Okay, now once you have the epoxide operates a lot like what we saw with the bromonium ion, right? It's going to sit on top or on bottom of the alkene, and what's going to happen is that gets protonated. Once that gets protonated, all of a sudden it's a really good leaving group. So then the molecule is subject to a nucleophilic attack, and of course, just like with the bromonium ion, the epoxide is blocking the top, so the nucleophile has to attack from the bottom. So you form your oxonium ion, that oxonium ion then gets deprotonated, and boom, you have your diol just there. Your anti-diol, because they're added from opposite sides. Again, this should be just kind of like similar here. You kind of see these intermediates here. We have the protonated epoxide, the bromonium, and the mercurinium ion all look very similar. You get ring strain, so that's reactive, plus one formal charge, means it's good as an electrophile. They're going to yield anti-products due to basically sterically blocking the nucleophilic attack from the top. Okay, now with syn dihydroxylation, so that's anti-dihydroxylation. There is also a way to add to the same side on the double bond, which is called syn dihydroxylation. So the OH and OH are both going to be on top. So the easiest way to do this is using osmium tetroxide, OSO4. It's osmium, look it up on the periodic table. You don't really hear about it much, and there's good reason for that. We'll talk about that on the next slide. But what happens is basically, you take this OSO4 minus, you have a nucleophilic attack of the pi bond onto this oxygen, and that's because this osmium is positively charged, so it's pulling the electron density towards itself. When that happens, the osmium-oxygen double bond breaks, leaving a lone pair on the osmium, And at the same time, this other osmium oxygen bond is going to do a nucleophilic attack on the other carbon, forming now like what's called a cyclic osmate ester. Now these all have to be on the same side. They have to attack, either from the top altogether or from the bottom altogether, because look, they're forming a cyclic product. So it just doesn't fit if you were to try to do it on opposite sides. So this is what's called the cyclic osmate ester. Now the reason for that is, this osmium still is double bonded to this oxygen here, single bonded to this oxygen, and that oxygen is then bonded to a carbon. So it's like if you close your eyes, you can see it as a ester. But this is the intermediate here, basically, that forms. Then once you take this, you can put it in a bisulfite or sulfite solution, and that basically removes the osmium and gives you your diol. Now there's a huge problem with osmium. Well, two huge problems. Number one, it's expensive. Number two, it's like one of the most toxic substances known to man, basically. It's like, it's the most poisonous of all poisons. Like, yeah, read the Wikipedia on it. It's really wild, like how toxic it really is. So that's no good. And in chemistry, we don't want to use the most toxic substances necessarily, because any toxic substances that get used get put out into the world, and you don't want that osmium to be mixed up with your medicine. Otherwise, your medicine's not going to do the job it should. So there are ways to get around it. If you use NMO, which is this guy right here, that's an alkyl peroxide, and it's a co-oxidant, and it basically helps this go very quickly. So you only need just a little bit of the osmium tetroxide. Yeah, so sorry, this is NMO, and this is an alkyl peroxide down here. Either way, that helps you just use catalytic amounts of the osmium. So permanganate can do the same thing, potassium permanganate, but you have to do it under very cold conditions. And as you can see, it's like the same thing, basically. You just manganese instead of osmium. But the problem is, like, it's extremely reactive. So if you do it at like room temperature, for example, it's just going to chew up the whole thing. So unfortunately, permanganate is not very useful for syn dihydroxylation. But if you have like a basic compound like this cyclohexene here, it can be useful. Okay. Now, I know we've gone through a lot of mechanisms, and there's a lot of mechanisms that you need to memorize and understand for this class. But here, I'm willing to give you one that I'm not going to make you memorize, which is what's called ozonolysis, or double bond cleavage. So this is, ozonolysis is basically you take an alkene, react it with ozone, and then you use a little bit of dimethyl sulfide to finish up the reaction. And what happens is, the way I always think about it is cut this double bond in half. And then what was the double bond? So here, let's use two different. So this guy, then you just put an oxygen here on both sides. So this half becomes this guy, and this half becomes this guy here. So a ketone and an aldehyde. So it's like you chop that double bond in half, and each side got an oxygen where the alkene was, to cap it off. So yeah, ozone, this is kind of unique. It's a very different one. Remember that ozone exists as a resonance hybrid. You probably had to do this way back in general chemistry, but hopefully you recall. And this is the mechanism. Again, I'm not going to make you memorize it, but we can walk it through just to kind of like get a good idea of what it looks like. What happens is basically you have a nucleophilic attack of the pi bond onto one of the oxygens. Then that breaks the oxygen-oxygen double bond, moving a lone pair onto the central one. And then the opposite oxygen, the one that has the negative formal charge, that's going to do a nucleophilic attack on the other carbon. So this is your ozonide here, where you have, again, 2 carbons, 3 oxygens, and they're all in a ring together. And this is then going to break. So what breaks is basically you form a carbon-oxygen double bond up here, and then a carbon-oxygen double bond down here, and then an oxygen-oxygen single bond here. Now this is where things actually get crazy. From this ozonide, after you break that all up, you get your ketone up top, and then your peroxy ketone down here. Excuse me. Then this negative formal charge oxygen is going to act as an electrophile, or a nucleophile, excuse me, on this carbonyl carbon. And at the same time, this carbon-oxygen double bond is going to form a new oxygen-carbon bond to the other carbonyl carbon. So that gives you your second ozonide here, where now all of a sudden the carbons are in between. You have a peroxide down here, and then just an ether up here. You had just a mild reducing agent, and then you isolate your two ketones in this case, ketones or aldehydes. This mild reducing agent, again, we usually use DMS, but you can also use zinc and water, so you might see that. Okay, so again, you don't have to memorize this mechanism, but it's interesting to walk it through. The main thing is you need to be able to use the reaction, right? And the reaction is going to go like this. We have some practice of this down here. Again, you split this in half, and basically you get an oxygen on this side and an oxygen on that side. That's how I always think of it. Okay, make sure to practice with the practice exercise down below. We're going to move on. The end of this chapter is basically just talking about the different types of synthetic techniques and strategies that you can use using addition, substitution, and elimination reactions. So that's where we're going to go next. I will see you very soon, and make sure you get some practice writing those mechanisms, okay? All right, bye-bye.